Okay, this is Mr. Weisword. We're talking about the AP summer assignment, AP Physics summer assignment, graphing equations. Right now we're looking at question number 57. We did question number 57 in the last video. I just wanted to talk a little bit about some of these graphs and blow them up a little bit. So I'm using Excel. Let's just look again at question C. If you were to plot y equals x squared, remember parabolas, these graceful arcing shapes, it would be a little bit, wouldn't do the parabola justice to say that it isn't symmetric and it's got a little bit of a kink and it's not quite smooth. The parabola is quite an amazing shape. And here it is in with a little bit more detail, a little bit more points. Notice though, of course, that what you've got is it goes through the point -1, 1, -1, 1 here, and it goes through the point 1, 1 here, and then -2, 4, and if I had kept plotting, it would go through the point 2, 4, somewhere over here, right? So those were the key points, and then of course we also had the point 0, 0. Those were the points that we picked, and we did a fairly, good job with our graph. The point is that if you want to graph things better, grab a computer. So now let's look at D. D was y equals the square root of x, just y equals the square root of x. And what we said was, again, it's this parabola shape. Now it's on its side. When you have x equals 1, you have this point 1 here as well. X equals 1, y equals 1, because the square root of 1 is 1. But you also have the square root of 1 is -1. And I didn't mean to, put that little mark there, but oh well, I did it. So, very important, these are y1, these are the negative roots, and these are the positive roots of your x values. So here's your x values in the first column. So that's question D, 57, part D. Yeah. Now part E. I wanted to do a comparison between y equals 1 over x, y equals 1 over x squared, and y equals 1 over the square root of x. You'll notice that they're all kind of what we'd say is negative powers of x. This is y equals x to the -1. This is y equals x to the -2. And this is y equals x to the -1/2. Those all have those all have a similar shape, and if we do those in Excel, let me just zoom in here a little bit. All right. Zooming in a little bit. All right. For y equals 1 over x, you have this graceful sloping line at x equals 0.5. You have y equals 2. At x equals 1, y equals 1. At x equals 2, y equals 1/2. 1/2 right here. And so these points right here are doing this kind of graceful slope, and that's fine. You could ask yourself, which curve gets smaller quicker past x equals 1? And I think you'd have to say that as the power of x increases in the denominator, it decreases quicker, excuse me. And as the power of x in the denominator gets smaller, so less than 1, it decreases slower. So let's walk through that real quick. Change my color here. Let's highlight pink here. So when I have 1 over x squared, when x equals, when x equals 0.5, y is up here at like 4. So that's a very high. So I'm on this curve right here. And this curve right here has again a point at x equals 1, y equals 1, and then it's dipping away much faster. So when x equals 2, y equals 1 over 2 squared, 1 over 4.25. That's definitely going, much faster here than the 1 over x curve. And then again, or let's switch gears to y equals 1 over the square root of x. So now here, when x equals 0.5, 1 over the square root of 0.5 is like 0.707, or well, it's less than 1.5. And then when x equals 1, 1 over the square root of 1 is 1. And notice that this curve right here, the yellow on blue, they're not decreasing as quickly. And that's because the square root does not get big as fast as x squared does. So I wanted to show that curve, and then I don't think I did a sine curve. What I wanted to do with the sine curve is basically show you that these numbers 2 pi, pi over 2, 3 pi over 2, those mean something, right? Because pi is 3.14, 3.14 divided by 2 is 1.5717. Okay, so we are going to put pi over 2 or pi sometimes because it's just easier, but you need to know that those are real numbers. Those are the radian degrees, where 0 is 0 radians, pi is 180 degrees, pi radians. So just know that that sine curve is a lot richer. All right, so here we go. Question number 59. Marbles in a cylinder. So what I have in my head is I've got a cylinder here. It's like a graduated cylinder. So it's got this cool base on it. And it's got rounded, and it's got these tick marks here that tell you how much water is in the cylinder. And the tick marks are good. And they help us, you know, if you have some water in there. So trying to draw some water in there, like some shaded in water here. You have a certain level. You'll read the level on the scale here. And then if I were to drop something, so in this case we're dropping in some kind of marble. Maybe I have another marble here. We would expect the water to go up, right? Because the volume of the water is being displaced by the marble, and so this level would go up as we add marbles. And so that's our intuition here. Let's do this. We're gonna I think what I did is I said this was 0 here, and this was 0 here. So this is 0, 0. And then we did 1, 2, 3, 4, 5, 6, 7. And what those numbers are is the number of marbles. So that's my independent variable. I can add as many marbles as I want, and what should be my responding variable or my changing variable, or the one that's going to be interesting in the lab, is that the water level is going to go up. So let's do this. Draw my y-axis here, and this is the water level, and this is the water level in milliliters. So I have, let's do 10, 20, 30, 40, 50, 60, 70, 80, 90. All right, so I've got 10, 20, 30, and we can just graph the data. So once I set up the graph, and I'm going to also do this in Excel in just a moment, so hang tight if you want to see that. So when I put in 3 marbles, I basically get a height of 58. So let's do 59 and be right tight on that. Let's go down a little bit. So 58, maybe right there. When I put in 4 marbles, I'm going to get 61. So that's just slightly above that line. When I put in 5 marbles, I'm going to have 63. So 5 marbles, 63 is not tight on 65. It's like right here. And then when I put in 6 marbles, I get 65. So that's dead on this one right here. And then when I put in 7 marbles, I get 68 or so. So that's a little bit below there, 68. Straight line or not? What do you think? Well, I'll tell you what. One of the ways that we do the straight line test is we say, how much is this changing as this changes? So this is the delta x. Delta x here is 1. Delta y is 3 in this case. And then from here to here, delta y is 2. And then from here to here, delta y is 2. And from here to here, delta y is 3. So ideally, you would like these numbers to not change if it was perfectly linear, but this is experimental data, so it's going to be a little bit wonky. What we should say is that the average, so the line of best fit goes through the average value. So take the average value of x. In stats, we say bar x. That's going to be the average x value. And that's going to be, in this case, if you add those up and then divide by 2, you will get the average is 5. So that's, sorry, not divide by 2, divide by 5. It's 3 plus 4, 7, plus 5, 12, plus 6, 18, plus 7, 25 divided by 5 is 5. Okay. And then the y bar, the average value for y, if you add these all up, and then divide by 5, you'll get the average is 63. You can double check me, or we'll double check in Excel. But that means the line of best fit has to go through this point right here. So maybe I draw a little. We're going to be fairly careful about this in this class. So I'm going to draw little point protectors. That means this is where this point is. That's telling you that dead in the middle of that circle is where the point is. So when I draw a line, you won't get confused and say, well, where was the point? So if I was to draw the line through there, I think it's going to go like this, right? Kind of close to those. Should go dead through that. Dang it. It should go dead through that point there. Maybe go above those, but below others. Okay. So there's my line of best fit. And you know, the curious thing about the line of best fit is that it predicts how much water was there if I didn't have any marbles in it, right? Because 0 marbles means I have this much water. And so I'm thinking it were somewhere between 45 and 50, maybe even 48 or something. So when it says here, tell me what the formula is, wow, you have to basically say, what's the average? So the formula for a line, y equals mx plus b, the y-intercept I'm thinking is like 48, so b is maybe 48 milliliters, so with no marbles. I did that by basically reading it off the graph, so read this off the graph. It's really the only way to do it right now. And also that the slope, so you know what I'm going to say about the slope, it's the average for these values. So the slope is 3, from there to there 2, and then 2, and then 3. So the average slope, let's do like an M bar. The average slope is going to be, you know, I'm predicting it's going to be 4.510. I'm predicting it's going to be like 2.5. And how did I get that? I said the slope for between a couple of points is 3, and another couple of points is 2, another couple of points is 1, and then I have 4 total segments. So that's 5, and 5 is 10, divided by 4 is 2.5. So I'm saying that the formula, let's see, water level, I'm going to be real stickler and say that you need to basically tell me what your variables mean, equals 2.5 milliliters per marble. And notice that this tells you how many milliliters each marble is, plus 48. Uh, 48 milliliters. So when you have 0 marbles, you have, oh shoot, 2.5 milliliters times the number of marbles. Pardon me a second while I fix this. Here's what I meant to say. In pure symbols, y equals 2.5 times x plus b. But y is milliliters water level. Water level in milliliters equals, I can put the units in parentheses, equals 2.5 milliliters per marble. And this is what I'd forgotten. Times the number of marbles plus 48 milliliters. Which is to say, if you have 0 marbles, you have 48 milliliters. That's your y-intercept. And if you have 1 marble, if you have 3 marbles, then you get to basically 3 times that. It's 15, 6, 7, 55, something like that. Yeah, 58 or something. Okay, cool. So let's write it here. So, no, I'm not going to write it again. I'm just going to say C over there on the side. See the box. See the red box. Ooh, and then they want an explanation. Haha. So I think they want this for the red box. And B, we said what B was 48. And then the explanation of the formula in words, that's the full, so let's do this in pink. So this pink, the pink rectangle is the explanation in words. Which means that your water level in milliliters is 2.5 milliliters per marble times the number of marbles plus 48 milliliters. And the meaning of the slope is the slope equals the volume of each marble. Assuming all the marbles are the same, may or may not be a good may or may not be a good assumption. And then the slope and the intercept is, I'll just write here intercept. Let me go down a little bit so you can see. Intercept is amount of water with no marbles. So hopefully you can see that. So that was good. Nice work. That was your assignment. I'm going to talk through Excel here real quick for question number 59 and 60. So check this out. I have here a setup for 59 and 60. I've got the number of marbles. Type that label right here. 3, 4, 5, 6, 7. I've got the water level. And that's 58, 61, 63, 65, 68. I can graph that like so. Insert, and I'm going to have it draw a scatter plot. Alright, and I'm going to have this go through 0. Alright, so now our graph shows, looks very similar to what we had. Going back here to our graph, looks very similar. Now in Excel, you can click to select the points, add a trend line. And then it's a linear trend line. And you can have Excel show me the equation and the r squared. And there you have it. All right, and then let's see. the trend line is our best fit. So let me highlight that. So we said the slope was something like 2.5, right? And then we said that the intercept was 48. So 51 is pretty close. Excel is doing a mathematical line of best fit, which is minimizing the error, the distance from the line to the points in our data set. And so it's doing a little bit better job. So if you have this answer, that means you did it in Excel. Nice work. If you did it by hand, something like what I said, that's good too. This would be probably the best answer, 2.4x plus 51. And what that means is when you go here, this is our prediction. So if you go that times 2.4 plus 51, you should get 58. And if you do that for all the points, you can see how far off we are. So we're a little low. Notice we're a little low on the second point. We're dead on the third point. For the fourth point, we're a little high. And then we're a little low, high, and then a little low on that point there. But that's basically what you see when you kind of zoom in on the line here, right? You can see we're below. So we're above, below, right on, above, and below again. Okay, so great job on your first assignment for AP Physics. Now we can get to work learning some physics.